Hello and welcome to this session on reinforcement learning, introduction and its relationship with ML, AI and optimization. So there has been a lot of confusion in the public literature with respect to what is reinforcement learning, what is supervised learning, unsupervised learning, but I think the key distinction that people are not paying much focus to is its relationship with AI and optimization. So let's get started. So let's first understand what is reinforcement learning. So reinforcement learning is nothing but a science to train agents using rewards and an environment, or train an agent against an environment using rewards. So this is depicted in this particular figure. So we have an agent and we have an environment. Environment sends a state to the agent, and if it is not at time t is equals to 0, then also a reward. In case if time is equals to 0, which means that we are initiating our and what is called as episode, then it will be only state that will be sent. And then the agent sees the state and maybe the reward if it is there, and determines the next action. It tells the environment that I'm taking this action, and correspondingly environment changes the state and also generates a reward and send it to the agent for training. Now let's try to understand it with the help of an example. Now suppose this is the grid world, okay, and or a maze, and your agent, you need to find out its way to the treasure, and it needs to avoid any of the ditches in between, in which case it loses a life or some points. So this agent, if we are starting and time is equals to 0, it will be presented with a state. The state could be simply the place where it is started from, and maybe the position of the grid. It doesn't knows anything about where the walls are, where the intersections are, and then the agent takes an action. The action in the could be in the terms of which particular opening, if any, it is taking. Or to be more minute, if there are like controls like left, right, top, bottom, then what control it is taking. In this particular problem, since we have only kept openings for the agent, and only the agent can only use some of the openings, suppose we say that we are using this particular route to start with. Okay, so this is our time is equals to 1. Okay, time is equals to 0 was this state, and then time is equals to 1 is here. Now in this particular case, we have not reached a final point. Okay, so there is no reward or no penalty, but in this particular case, the agent can actually get stuck because it doesn't have any reward or penalty, and our objective is to reach here in the minimum possible turns. So we can say that for each turn that the agent takes, we can give a penalty of -1 or a reward of -1, such that we can enforce the agent to get to its final state in the least possible time. And after reaching here, the state is this particular position in the matrix, and the openings available are this and this. So this is also the part of the state. So in this particular case, the state is where it is and what are the openings that it has. Okay, this openings can be a list. Okay, so this is our state, and then agent again decides which particular opening it has to take, this one or this one, and then this will be time step is equals to 2, and again a penalty of -1. So in the final state, suppose the agent reach over here. Okay, so this is say step is equals to n, and if it decides to actually go here, it will get the treasure. So at n plus 1, suppose it gets the treasure, we can give it the reward of the treasure. So suppose the reward is anything, so r big we can call it, some number if you want to assume, like 10 to the power 3 or something like that. And Then if it reaches a penalty, suppose if it is here and reaches penalty, we can give like a big minus reward. So what the agent will learn over the episodes or over the steps in this particular episode is how to maximize this reward. So this what we did was say one episode, and then we reset the agent. Resetting position could be anything. So suppose in episode 2 we start from here. Okay, so this is episode 2's start position. Okay, so episode 3 suppose starts from here. Okay, or we can have like all the episodes will start from here and the agent can find out. So depending upon whatever condition, so till agent doesn't collides an endpoint, it loses a life or it reaches a treasure, we can, or it reaches some maximum number of steps that is allowed to take, then we will call it an episode, and we will allow agents to train across multiple episodes. So this is reinforcement learning. So now we come to our basic question of what is reinforcement learning and what is the relationship with different types of machine learning. So this picture is very interesting. So machine learning is actually a part, or artificial intelligence is actually a part of machine learning. Some people actually say that ML is a part of AI, but this is more of like a marketing terminology that you can say that AI is more, you can say, value added, and you can keep machine learning in there to denote that all the classical models will be in machine learning and all the deep learning and other models will be in the AI. But academically, this is the wrong definition. So academically, the definition of machine learning is anything that makes a system intelligent or makes is the art of making the machines learn. So there are two parts. One is machine, the second is learning. In machine, obviously, these are could be our computers, robots, or anything, any type of machine. So let's assume it's a computer, okay, or it's an automation system or robot, anything. The learning could be of two types. So the first type may be a rule-based learning. Okay, the second type could be self-learning. So one system over here is a rule-based learning. Okay, all the remaining of this that we are seeing is self-learning. Now self-learning could differ. So the most prominent types of self-learning that we have seen in the case of machine learning is maybe supervised learning or maybe unsupervised learning. So all the classical examples that you have seen like random forest or maybe logistic regression or maybe linear regressions, these are all examples of your supervised learning. It could be a categorical learning or continuous learning depending upon what you're saying. All the other forms that you might be have learned about, say clustering or anomaly detection or maybe association mining, these are unsupervised learning. Why? Because we do not have a label. So the primary distinction between them is that supervised learning has a data record, okay, or a set of features that we call a feature vector x, that can have like x1, x2, and so on and so forth, and we have a corresponding y. Okay, and our objective is to map x to y such that if a new x comes, we can actually predict the value of new y over here. Whereas in case of unsupervised learning, we essentially do not have a target. Okay, and our only purpose over here is to reveal patterns within the data, and depending upon what type of pattern we are finding, we will choose one category of algorithms over there. Okay, so it will have only x vectors with some x features but no y. Okay, then there is deep learning. Now deep learning is not a different type of machine learning, but it will have like a supervised learning and unsupervised learning. The only distinguishing factor is that it will be doing everything, whether it's an unsupervised learning or a supervised learning, through a network of neurons. Okay, so you will have deep networks of neurons. or artificial neurons, you can say. And it can use these networks to do something like a supervised learning. Suppose you have MLP-DNN, just used for general structured data and any predictions on that, and you can do any type of prediction over here. It can be a categorical prediction or it can be a linear regression sort of a problem. Then there are CNNs, RNNs for different types of objects. So this is for image, and then RNNs for say text or speeches. So there will be overlap between your over supervised and unsupervised and deep learning. So there could be a non-deep learning variant like these we have pointed out, and these are the deep learning variants for supervised. Similarly, for unsupervised, deep learning can be something like an autoencoder, restricted Boltzmann machine, something like that, and they'll have other type of unsupervised learning as well. Then comes another field of machine learning, completely different field of machine learning called artificial intelligence. Artificial intelligence is nothing but the science to train intelligent agents. So this is a classical definition from one of the very famous old book called by Peter Norvig, which is considered as like the Bible for AI. Science of teaching intelligent agents. Now, even intelligent here is not used in colloquial terms, but it has different meanings. One of the prominent meanings in academics is if your agent can determine rationality or human-like decision making. Okay. Then we can call it intelligent, and there are different parameters to determine if it is rational or human like. And then the second point is agents. And there can be different types of artificial intelligence, but one of the types is reinforcement learning. So reinforcement learning is a subcomponent of artificial intelligence. Again, reinforcement learning could be of two types. One is a classical reinforcement learning, and then the second may use deep learning and other models, which would be in this case deep reinforcement learning or approximation function based reinforcement learning. We'll discuss different types of reinforcement learning in detail in another session, but let's move on to discover more important and say lighter facts about reinforcement learning. So now that we have understood what is reinforcement learning in brief and where it's a part of artificial intelligence, let's get deep into artificial intelligence. So in artificial intelligence, there is a system called reward systems of training agents, in which you determine a reward that you will give to an agent if it accomplishes a particular task. Now this reward could be a positive reward or a negative reward. Okay. And you can determine when you have to give it. And you can determine a reward function. So if you have multiple types of things that you want this agent to accomplish, so for example, in a previous example, we wanted the agent to, number one, reach to the treasure point, okay, and number two, we wanted to do that in the minimum possible turns. So we kept a reward for here and a negative reward in the case of a penalty, you can say, in for the turns, and a reward function comprised of both of these points. Okay, so what is a reward may be given by a reward function, and the agent would try to maximize this. Now, what are intelligent agents? So intelligent agents, as we discussed earlier, are the ones that can have rational thinking and human level decision making. We'll discuss more about it in the next topic that we'll be covering on optimization. But we'll cover some differences on supervised learning and the reinforcement learning to determine what is rational thinking and what is human level decision making. Okay. So reinforcement learning comes into the overlap agent between your reward systems and your intelligent agents. So it makes intelligent agents a basis on reward functions. So now take a moment in determining our rational thinking and your human level decision making. Okay, so let's assume again I have a game or a maze of backgammon. Okay, or you can take it a maze that we discovered earlier. Now what we are trying to do over here is that we are trying to find out the treasure based on what agent could do or where it could go. You can essentially make a sort of a supervised learning problem on this. So suppose if I have a classification problem and the input to the classifications could be exactly the state that we talked about, and our state was nothing but our position. Okay, and maybe the openings, where the openings are. So there the openings is say top left, bottom right. Okay, and you can say 1 0 something like that, and this could be your ID, position ID. But the problem over here is I do not have a Y. The only Y I could get or the reward in this particular case is at the end. So these type of problems, it is not even possible to solve by supervised learning. Okay, but let's assume some domain where it is not about two long trajectories, and let's simplify it also that you're not getting the reward only at the end, but you're getting some rewards in between also. Okay, so suppose now you have the game of basketball and you are trying to aim your ball inside this particular basket. Okay, and suppose this basket is moving and you need to determine say at the first instance the angle at which you can throw the ball. Now this is a problem that you can solve both by reinforcement learning maybe and also by supervised learning, but what is the difference in both the cases? So if I'm trying to model this problem as a supervised learning problem, I can put my state as an X vector, which is nothing but the position of the basket, the direction in which it is going, and the speed at which it is going. Okay, and maybe the position of the person who is trying to throw it. Okay, and from there my Y vector could be the angle at which we have to throw it. Okay, and since this is not exactly either a categorical problem because angle is actually a continuous variable that we are trying to predict, but the problem with putting it as a continuous variable would be that suppose the basket changes from here to there, it is not a continuous sort of a signal that changes the direction. So you may call it more as a nominal sort of a thing. In fact, it is not even ordinal because it is not say angle x is greater than angle y in terms of where it is going. So let's assume that you are giving like a minute categorical problem. Okay, so maybe my categories here is say angle from 0 to 360 or 0 to 2 pi in terms of radius with say pi by 100 as the breakpoint. So I have 0 pi, okay, then I have pi by 100 and so on as my categories. Okay, and this is what I'm trying to predict. Now you have already guessed the problem that is going to come. Okay, and that is why this will not work. But suppose if this would have worked, so suppose now we say that the only angles allowed to throw the ball is maybe say 0 degree, 30 degree, 60 degree, or it is between say minus 45 to plus 45. So 0, 5, 10, or say minus 5, 0, and 5, and the basket is only moving between this case. So there you can limit the number of your angles in this particular case. Suppose now here left with only 15 angles, minus 5, minus 4, and so on and so forth, or plus 1, 16 angles. And for if you want to solve it this particular way, you'll require a lot of data for exact mappings of this, which is still fine, we can get that. But now suppose we change the problem slightly and you bring it to a real life problem. So in the real life you also have to see at what with what force you have to throw the ball at that particular angle, because I can actually increase my force and take a parabolic path, I can decrease my force and take this particular path. Both are correct, both will actually do a basket depending upon how much is the risk in what conditions. So if there is a lot of wind, I may actually increase the force and send it directly over here to actually beat the wind, or to have lesser problems because of wind, get greater accuracy. Versus if it is a calm thing, I can actually take this particular route. So there could be different other factors that is coming in real life which will not be able to encounter here. And in that particular case, we now have two objectives, y1 and y2, which is the angle and the strength or the force. Now you can easily understand this is not a supervised learning problem at all, at least till we are not actually doing it in a combined manner, and then we'll not have enough data or opportunities to do it in the combined manner. The second problem that we have seen is that we require a lot of existing data to make any sort of a supervised learning model, and that existing data should be sufficient to cover most of the cases that we are trying to say, or at least make a model that can work with extrapolation on those things. Because if there is a lot of interaction and the conditions are changing within the data gaps, then you cannot pick a very good supervised learning problem. Whereas in the case of reinforcement learning, what we provide to reinforcement learning is not essentially a data what that we're providing in supervised learning, but we are providing it an environment. Okay, and the agent, instead of consuming directly the data to learn, tries to interact with the environment on its own and tries to see what happens if it does something. So this data that we are talking about, this the agent would be generating, or this is the state, and whatever is this particular data that we are talking about, angle and combination of both angle and force on its own, and it will be sending the environment, and the environment will see what is the ideal state of the reward that it should be giving. And you can have rewards like if it is landing into the central square, then you can give it some points, and if it is also hitting into the basket, then some other points. And if it hits the basket even with the condition of wind and other things, then you can give it extra points, and then you can actually add your wind directions and wind speed and your state wind direction. The difference between reinforcement learning and unsupervised learning is quite trivial. Most of the people have problem between understanding the difference between reinforcement learning and supervised learning, because in some of the cases, at least very trivial cases, you can actually solve it by supervised learning, and in those conditions it will be actually overkill to solve that problem by reinforcement learning. The only place where you can actually use reinforcement learning, despite the fact that it's a typical supervised learning or unsupervised learning problem, is so when we find something which is mathematically intractable, or you do not find a convex function or a concave function or multiple convex or concave function that doesn't have a differential, it couldn't be differentiated very easily. That is also some places where you can employ reinforcement learning to accompany or complement your supervised and supervised learning. Let's now understand the difference between your unsupervised learning and your reinforcement learning. So unsupervised learning is also you are given an x vector, which in our case is synonymous to our state, say in case of reinforcement learning. And in unsupervised also you're not given a y vector, and in reinforcement learning also you're not given a y vector. But the difference over here is that in unsupervised learning you do not require a y vector. Everything is like patterns within x. You're trying to find patterns within x. Okay, and depending upon what type of patterns you are finding, you can actually put it like I can find a cluster sort of a thing which are close or similar items, or I can find anomalies and so on and so forth. Whereas in the reinforcement learning you actually have a specific goal. Okay, and based on that goal we'll keep a reward. There can be multiple goals, say y1 and y2 and y3. Based on that we keep a reward. And the reason why we are not giving this beforehand is because this would be computed or discovered when the agent is interacting with the environment. So instead of giving this and this separately, we have got an environment that will generate our x vector or other state, and the agent will actually generate these things to explore what happens if it takes a particular action. So these y's are your actions, or your y's would be generated by your agent instead of being provided beforehand, and then you will get a corresponding reward to see how good was that y. So this is the measure of how good is that y, and then the agent will learn a more optimal y. In fact, if this is the case, then reinforcement learning is more similar to optimization as compared to. So if this is the case, then reinforcement learning is actually more similar to optimization as compared to our supervised or unsupervised machine learning. So let's try to understand why this is so. So in both of the cases, both either in optimization or in reinforcement learning, at least for some of the type of problems, what we are trying to do is we are finding a good control mechanism. Okay, so let's take an example over here. So suppose I have multiple machines which are working in synchronization. Okay, and if any changes is brought to one particular machine, it can actually change other machines and so on and so forth. Okay. So these are all interlinked machines, and we have a controller over here that may have an input from all the sensors on all these machines. So each machine could have multiple types of sensors, and the controller in turn can change some of the parameters of some of these machines. So suppose this has a parameter that the controller can change. This has two parameters that the controller can change. And this doesn't has any parameter that the controller can change. Okay, and after it changes a particular parameter, it can get a feedback from the machines, which is nothing but the revised reading of the sensors, okay, which will be coming in this particular format, and then the controller can again change some of these set points to get to the final control. So both of these mechanisms, whether the optimization or reinforcement learning, can work to make this sort of a control systems. And if this looks a trivial example to you, assume a self-driving car. In fact, a self-driving car is also a control problem. The only factor is that these MVs are very high in that you can take a lot of different actions. You can apply brakes at different levels. You can do change the steering directions. You can change your speed, and all these sensors could be your camera sensors, your lidar, and everything that is coming, that is exposed to a self-driving car. But that is also a control problems. So both of these could be actually seen as a control problem. If we are trying to solve it as an optimization, what we'll do is we'll do a model prediction learning. Okay, so we can make a models of all of these things, which will be completely mathematical models. And if this is so, we need to know everything about these machines and the interaction of all these sensors beforehand. Okay, so all data needs to be converted into a mathematics. That mathematics will make a model, and then we will optimize that model again using some other mathematics to give us a optimal plane and boundaries where we'll find the most optimal points. Okay, and then these most optimal points would be used to drive our MVs. Okay, so now you have guessed what is the difference between optimization and reinforcement learning. To reinforcement learning, obviously we have not given any of the data, but we have given an environment that can mimic this sort of a system. And in fact, the environment could be this real system as well, depending upon how safe it is to give it to the reinforcement learning agent, because the agent in the starting would not know anything. It can take any random actions, because of which you can have some problem with these machines. Okay, so it is given a dummy system, but it could be also given a real life system. For example, in the case of self-driving car, it is very dangerous to actually give it the car itself to drive, so you'll be giving it a simulated environment. Whereas if these machines are not something that they can go wrong with these MVs that is given, then you can actually give these machine control directly, and you can keep reading the sensor reading that is coming from that, which will be the new state that is coming. So to reinforcement learning, it doesn't need to have the complete data or even a mathematical model. So one is the data part, but even from the data, the optimization would require a lot of understanding of the mathematical data, which is the distributions of it, the interactions of distributions, and in these cases even the distribution might not be steady, so they might be actually changing dynamically. Okay, but for reinforcement learning, it can actually learn all of these things on its own. So if the problem is very simple, you may actually do it with optimization easily, but if the problem is more complex or it is more dynamic, then reinforcement learning might be a better choice. Or the problem is something where the mathematics couldn't be obtained, or the mathematics is too complex, the mathematics is intractable. So even if you can see what is the mathematics coming out to be, but you cannot not go to the second step to optimize that particular mathematics, then also you require reinforcement learning. Okay, so this is the short introduction about reinforcement learning and its relationship with artificial intelligence, machine learning, unsupervised learning, supervised learning, and especially optimization. So hope this is helpful. In the next session, we'll cover some differences, and we'll go inside differences of optimization and reinforcement learning. And in one of the other sessions, we'll cover the different types of reinforcement learning. So hope you enjoyed it. Please like it and subscribe to the channel. Thank you.